let's turn to the event at hand today, our Electrification Symposium. To me, it feels like the word electrification could be the word of the year, or the phrase electrify everything, the call to action of our moment. We hear them everywhere, and for good reason. We must move off of fossil fuels, generate clean electricity, and power our newly decarbonized global economy, and do it fast. But if I may, I tend to think of the electrification slogans a bit as if we said, let's get to the top of the world, so let's hike up Mount Everest. No problem. But summiting Everest, like electrifying everything, is easier said than done. What if there's a bottleneck on the path due to overdemand and lack of capacity? What if you need to climb in less than optimal weather? What if your gear is too heavy or your poor physical condition demands high intensity care, putting others at risk? Simply throwing money at the problem is no guarantee of getting there. As we would acknowledge the very tangible limits and optimize our climb up Everest, we also need to do so with our buildings. There's no magic carpet to get us there. And as we'll see today, the Passive House Standards recognizes the limits of our all-electric future and empowers us to tune our buildings, design to overcome them and deliver the comfortable, efficient, resilient, affordable buildings that we know are possible, because we all have to get to the top of Everest together. So I hope you'll please pay close attention. Put your questions in the chat. During the panel discussions at the end of the two sections, we'll incorporate your questions into conversations. And I expect more than a few will also be answered as we go along. If you like continuing education credits, please email in to training@passivehousenetwork.org. A quick look at our agenda. Immediately following, we'll first have Jessica Grove-Smith, a physicist and a managing director of the Passive House Institute in Darmstadt, set the stage by outlining the transformative approach driving passive house electrification within the Passive House Standard. Then Bronwyn Berry, an architect and principal of her firm, Passive House BB, will illustrate her evolving strategies in designing all-electric passive house homes in California. Tim Ian, also an architect and principal of TE Studio, will take us on a deep dive into his electric home in Minneapolis, Minnesota. After the presentations, we'll have a panel discussion, a talk incorporating your questions from the chat. After that first section, we'll take a quick 10-minute break, stretch, get some water, and then we'll come back. And first, we're going to hit it off with the trailblazing all-electric Passive House Hotel Marcel in New Haven, Connecticut, presented by its architect, developer, owner, and operator, Bruce Becker. Then Dylan Martello, Passive House expert at Stephen Winter Associates, will explore critical strategies in making multifamily buildings all-electric. And our final presentation will jump to statewide utility scale and the perspective on all this from Paul Ormond, an engineer at Massachusetts DOER, who is leading the movement in that state to crush the heating demand. We'll end with the final panel discussion, and we'll be on our way.
So it's great to be here. I'm joining you from Germany, from Darmstadt, on this great Thursday afternoon on this really important topic of electrification. It's always a pro and a con of going first in these kind of sessions. This is an event which is fully packed of great speakers and content on a really, really up-to-date, important topic. I really liked your analogy to Mount Everest. I know the challenges that we have to face when we speak about electrification as a big term. There are really a lot of nuances to dive into in order to get this right and really achieve our goal of sustainable electrification. So I'll do my best to set the scene here and talk about kind of how is electrification addressed from within the Passive House Standard, how do we deal with it? and how passive house or Enefit or retrofit can really leverage and help us for a sustainable electrification and successful decarbonization. So this whole topic of electrification and why it's needed and that it's needed is something that I'm going to set as a kind of given without diving into details. There are studies on it. We also did a lot of analysis specifically in the context of Germany, but that's not part of the discussion that I want to address today. The only mention here that I do want to emphasize is this is a crucial piece towards a clean, sustainable, renewable energy supply. And that's really at the bottom, or a big part of what we mean by electrification, right? A big part of renewable energy is electricity, it's solar, it's wind, it's hydropower. So when we talk about electrification, what we mean as a big part of that is a transition of our energy supply from fossil fuel-based to renewable energy resources. And when we think about that, when we keep that in mind, it makes it much easier and much more tangible to help us guide what are the things that we have to look out for in that context of electrification. It won't work to just electrify everything without thinking about the implications. What are the steps that we need to really make this a successful story, given the limitations that we have physically in terms of space, in terms of infrastructure limitations, in terms of cost, in terms of time trying to do this quickly. So we had to talk about electrification, but more specifically, we had to talk about buildings and electrification. So how does the trend for electrification influence building design? Or ask the other way around, what role do buildings play on this important journey of electrification? There's always the building design side in terms of how much energy do we need, what kind of systems do we use? And there's the big trend towards heat pump, obviously, in this context. And there's obviously the side of electricity and energy supply, which is in the context of buildings, typically and most dominantly PV. Now, when I was preparing this presentation, I read one of the most recent newsletters and updates from the blogger Lloyd Alter, and I couldn't have picked the words better, so I chose just to use his quote. And he says, if we're going to have a chance of electrifying everything and running on renewables, then we really have to reduce demand and shave the peaks. Those are really the two crucial aspects that it come down to. Crushing those peak loads, really bringing them down and reducing the need for electricity overall. And this is where Passive House and Enefit really come into play, because they do exactly that. They address these two topics, bringing down the peak loads and bringing down generally our energy demand. And I'm going to dive into a little bit more detail on both of those topics, kicking off with reducing energy demand, speak about that a little bit first. And the most important, or the obvious point here is that we do have limitations in terms of space. How fast and how much renewable can we actually build up in order to provide the same energy that is currently being provided through other resources, mainly through fossil fuels? That's a large amount of energy. And building a completely new infrastructure to provide that through renewables and electricity, it has to be limited, it has to be reduced, otherwise this becomes absolutely unfeasible. So a massive reduction plays a big part in terms of actually being able to achieve any kind of successful electrification. And there's a little bit more to it, not a little bit actually, a really important part of it. And that is that with renewables, timing is really, really important. They're not something that is just available when we need it. Renewable electricity is available when the sun shines or when the wind blows. So there's this whole topic of energy storage, which becomes a really important part of the storage. Of the story. Batteries, short-term storage is fairly easy to solve. Technology evolves, there's a lot available. But we have that whole seasonal topic and long-term energy storage to think about. And in a way, that's one of the elephants in the room that is kind of there, but not spoken enough about and not addressed enough about in terms of how do we deal with it? How can we make sure that we provide that kind of seasonal storage and that our infrastructure can cope with it, that our demand side is optimized, that it doesn't create massive amounts of need for seasonal storage. So again, Passive House for new builds or Enefit for retrofit can really, really help with this, because they really address bringing down the energy demand in winter, for example, for heating. They really, really bring that energy demand down. So we can see, if I just got on my laser pointer, on the examples shown on this slide, on the left-hand side, it's here just a typical net zero single family house. In red, we see the heating energy demand curve. in yellow, the production. So this is net zero, but we have that massive discrepancy between our supply and our demand. Here we have the passive house example. So you see how it really brings down that energy demand. With the same amount of PV, we're easily in a surplus. We can provide more to the grid and help cover some of those seasonal kind of storage issues. Or if we have the same net zero goal, it means having to bring a lot less PV to the grid. The other topic to speak about is our peak loads. With a passive house, you are by core definition going to have significantly reduced peak loads. And what we see here on a graph is an example for the summer case. This is absolutely great news for utilities, and it's a great news for electrification. It's a really important part of the story. So on the left-hand side here is the peak loads for a cooling case, where we have massive cooling peaks on a daily basis, versus in a passive house, which is energy efficient, we've really brought down the demand, but we've also really substantially and significantly brought down the peaks. We don't have those peaks every day, which the utilities, the grid has to deal with, and the demand or the loads are on a much more stable basis. There's an extra benefit that comes with this, which is really important to point out. Passive house buildings, energy efficient buildings, have much more inertia, right? They're much slower in a way to react. They're not so sensitive of having to get the right amount of heating or the right amount of cooling at a specific certain of time. So that gives them resilience. It gives them resilience, or gives us as a society resilience in different ways. One is that it gives us resilience in terms of much more stable temperatures in the building. And if there were to be a power cut, if there are problems, then this example shows that the temperature in a passive house stays very stable, even if there's no heat supply. And whereas in a normal building code in Germany, it drops much faster, and in an existing building, we very quickly get into areas that are uncomfortable. So this is thermal resilience, it's energy resilience. So a really important aspect to all of this. It also means that we have much more flexibility in terms of actually using our buildings sort of as storage as well, because it doesn't matter so much when we introduce the heat. It can be shifted by a few hours, maybe even a day, and still you're maintaining comfortable conditions within the building, which can really help to stabilize and run the grid. So shifting gears a little bit, what I've spoken about so far is reducing our energy demand and reducing our peak loads. Both of those are fundamental and core parts of the passive house definition of what passive house has always been about, in addition to kind of the building physics and comfort requirements. But there's a second and kind of extra tier to all of this. We need to look beyond just the heating and cooling. Ultimately, we need to look at the total energy efficiency, right? The total energy demand of the buildings. And that's done in the passive house, but also other standards by putting a limit, or by looking at the total energy demand of a project. So the heating, the cooling, but also your domestic hot water, your auxiliary, but also your household and any other uses that we have within the building. And here it becomes a little bit tricky. And here is where passive house has really developed a new solution to address all of the topic of electrification and renewable energy supply. Because the tricky question here is, what kind of indicator actually works well for that total energy assessment? And conventionally nowadays, and in the past, we've used and we've become used to using indicators such as source energy, which is fossil fuel based, or CO2 equivalents, which are both valid. They both have their historical context. They're both really interesting factors, but neither of them address the topics of electrified renewable energy grid. Neither of them incentivize in terms of we need to make sure we reduce our demand for renewables overall, and neither of them address the topics of seasonal mismatch or of peak loads. So an alternative is really needed in the passive house world, but also beyond, in terms of what tool can we use to guide our building design. And this is where PHI, a few years back, 2015 now, so almost 10 years ago, developed a scheme of PER. We call it Renewable Primary Energy, PER. And PER is, from its methodology, it's similar to kind of source site energy conversion, but fully in the context of a renewable energy supply. So the PER conversion factors that we use to convert from actual site energy by the building to the PER demand, they reflect how much renewable energy you'd have to feed into the grid on this side here in order to match your site energy demand on the building, taking into account that you can't avoid it. You are going to have losses along the way, either through battery storage to cover a couple of hours or days, or for the more long-term storage for the seasonal. There are different technologies being spoken about. I won't dive into the details of why we chose the methane solution shown here. It doesn't really matter because overall the efficiency of these seasonal long-term storage is only about 30%. So you're losing a lot of energy for anything that has to be stored for a long period of time. So this is the PER scheme that we've developed as Passive House Institute. And the idea is that you have weighting factors that actually give you an indication for your building design in terms of what is your amount of renewable energy, what is your sustainable use of renewable energy resources. It very, very quickly became apparent when we were doing the analysis that the actual timing between when does the energy demand occur and when are the renewable energies available is the driving factor for all of this efficiency of providing electrification or providing renewable energy, primary energy. We did a lot of simulations worldwide for different building scenarios, for different efficiency levels to derive these PER factors. And in the end, what has been implemented is that we have different PER factors for different locations, depending on the climate and depending on the renewable energy availability, but also different weighting factors for different use of the electricity. So your efficiency is going to be much worse for heating, where there's a huge mismatch between what's available and what you need, versus cooling, where quite often PV is available at the time when you need it for cooling. So all of these factors are integrated into PHBP, into the Passive House Planning Package, and they become part of sort of the climatic boundary condition for your energy modeling and give you a methodology for localized, regionalized electrification or decarbonization in a way. Right? How do I locally optimize my building for it to match up well with a renewable energy supply? So far, I've spoken about electricity in terms of PER, which is the main energy carrier, right, in terms of renewable energy supply. As explained, that depends on climate and on consumers. Obviously, in reality, not all buildings are going to electrify immediately, and we also have to look at how do we rate other energies within the PER scheme. It's beyond the scope of this presentation, but I did briefly want to show them and point them out because it becomes relevant for the discussion of how PER guides design compared to existing source energy ratings. So basically in the PER scheme, we rate all of energy carriers as if they were fully renewable. So gas, for example, becomes rated within the efficiency of it actually being power to gas. So gas created originally from renewable electricity. And I'm happy to answer more questions in the chat or afterwards about this. I'm going to skip it now in terms of time and actually dive into more the implications of what PER does and how it supports us in those decisions of electrification. So what we see here is in the context of the US and Canada, the source site ratios taken from the portfolio from the Energy Star portfolio. And you can see that the factors are quite high for electricity grid purchase and quite low for the fossil fuels typically commonly used for natural gas or even fuel oil. Whereas in the PER scheme, the factors for electricity, they vary depending on use on climate between 1 and 2, whereas the factors for gas and for oil are much higher, 1.75 for gas and 2.3 for oil. This is the same information, but just shown as a graph to make it a bit visually easier to understand. Orange is for the US and the light orange for Canada. And you can see, in the PER scheme, electricity is rated much more favorable, whereas in the current schemes, source to site, it's the fossil fuels that get encouraged and incentivized with these weighting factors. Applying this to an actual building, this is an exercise carried out with the PHBP based on a certified passive house project in California. You can look it up on the database if you want to learn more about this project. It's a single family house. And if we just look at the total primary energy implications for different heat systems for this specific project, blue is the PER results and red is the PE or the source energy results. And you can see that the PER really says that the gas solution, the gas furnace, is the worst, whereas your direct electric just about hits the target, not quite, but your best solution is definitely the heat pump. So it encourages you away from the gas solutions, away from the fossil fuels, towards your electrical solutions, ideally heat pump solutions. So that's what PER implies when you use it as part of your building design and choices for systems. PR is really important and applicable generally, and we'd like to see it pick up also outside of the passive house scheme to really make these aspects visible, and the importance of energy efficiency more integral of the whole building design processes. In terms of the passive house quality assurance, PER is applied in terms of the categorization of 3 certification tiers. So we have Passive House Classic, the traditional one that we know, and then for Plus and Premium, the fundamental requirements are the same in terms of very low peak loads, very low energy demand. But on top of that, for the higher tiers, for Plus and Premium, we're calling for an increased overall efficiency, so lower PER demand, and we're calling for a certain amount of renewable energy generation. Renewable energy generation is obviously the other side of this very same coin of electrification, and a very commonly used goal here is net zero. It's a simple and attractive concept. I get it, I understand it, but it can be very misleading. It ignores all of those aspects that I spoke about earlier regarding peak loads, regarding looking at seasonal storage and losses, and just leaves utilities to deal with these kind of problems. So as you see on the right-hand side indicated there, that the PER scheme shows us that actually to reach true net zero, all of this is needed in addition in order to cover your losses that you have along the way. So in the PER approach, we or PER methodology, we take a slightly different approach to renewable energy generation. Instead of looking at net zero for that specific building itself, we do an independent rating for the energy supply. So just rating the amount of renewable energies that you're providing with respect to the footprint that you're occupying for that building, as indicated by this graph here. That is what the passive house or the PER schemes uses for PER rating. Now, this is all a very big topic, and I realize this has been a very quick run through, so I just wanted to point out a few resources to dig a little bit deeper and learn more about the PER scheme. The go-to to get started is Passipedia, and then there's a landing page there for PER that'll take you through a lot of things that I've spoken about, but also kind of more in-depth information on how we develop PER and some more examples of how this gets implemented. Not all passive house and Enefit projects nowadays are fully electrified, but it is certainly an increasing trend that we're seeing. We'll hear about some really exciting trends and some really great projects from US context later today that I really look forward to. For those of you who are not yet familiar with our online passive house database, I encourage you to take a look. It's a fantastic resource to get inspired from projects that have been implemented, and you can use this to find projects that are of most interest to you by using the filters, for example, looking for Plus or Premium passive house or Enefit projects, or looking for search terms such as heat pump, which will point you in the direction of projects that have implemented heat pump or electrified solutions. Last, but certainly not least, I wanted to pick up one specific project, and since I'm based in Germany, I've picked out a German project to present to you. This is a quick case study. It's actually an Enefit project. So it's a retrofit project of a multi-family in Cologne. On the left-hand side here, you see what it looked like before. On the right-hand side is what it is now. And here you see the roof covered with PV. It's a deep energy and actually prefab retrofit, originally from 1961 with no insulation, has 4 stories and 16 units in total. And the goal was really, really challenging to do a serial retrofit in a very short period of time to net zero of an occupied building. And the approach was Energiesprong, but to the Enefit efficiency level. An interesting aspect here, also part of electrification, is ventilation, a big part also of the passive house concept. In this case, the ventilation units were integrated into those prefab facades elements brought as part of the retrofit solution. It's an all-electric, so it's now served, it wasn't previously, but it's now served by 2 air source heat pumps for the heating and the domestic hot water. In this case, they weren't able to implement a heat pump solution just for logistics and cost reasons, but they've upgraded basically the electric tankless water heaters. The numbers show that they do achieve net zero overall over the course of the year, but only due to the really high efficiency levels to the NFIT level that were implemented. It's a certified Passive House Plus. On the right-hand side here, you see over the course of the year exactly that topic that I mentioned earlier in terms of the difficulty that sometimes of the year you're overproducing through the PV, and other parts of the year you have a high demand, but you don't have enough electricity available from the building itself. So that entire challenge of net zero and balancing out the storage that has to be provided somehow, somewhere within the grid. So as I mentioned, we approach that differently in the Passive House certification scheme. We don't do net zero. We don't try to match your absolute energy production with your demand, but we rate them independently. So this is a screenshot from the PHPP showing where the project has achieved your Passive House Plus standard indicated by the dot here. This is the axis showing the efficiency levels it reached. So in order to reach plus, it has to be below this line. And in order to, on this axis, independently with respect to the footprint, it shows how much electricity it's producing, which is very high because most of that roof is covered by PV. There's a lot more to talk about, but that brings me to the end of my presentation. I'm excited to hand it over to the next speakers and learn about their projects. As core kind of message and takeaway, I think I just wanted to highlight that energy efficiency is really an enabler, but more than that, it's a prerequisite for our sustainable electrification. And Passive House and NFIT can really set us up and leverage those challenges and set us up for success. So thank you from my side. I look forward to the discussions. And for now, I hand over to Bronwyn.
Yeah, fantastic. Thank you, Jessica.
So, well, that was a good overview, Jessica. Thank you so much. Plenty to dig into there. And today I am going to really focus specifically on a bunch of projects that I've been working on in California to really kind of deep dive into specifics of the HVAC systems, which are primarily, in fact, all electric projects in California, with the exception of one very early project. My Passive House journey started in 2008, but I really kind of started going back to doing design in 2011. In conjunction with Alan Gilliland at One Sky Homes. So we marketed ourselves as design build. He retired in 2019. So the projects from 2019 to now are I've been working on my own in conjunction with a host of other builders. And obviously crystal ball gazing is well out of my purview, but we'll give it a stab. So I'm going to start with 3 projects that Alan and I worked on, lots of monitoring and data collection on these. We really were able to do some really innovative stuff on these projects. And I'll start with this one. The first Sunnyvale project was one that we really finished in 2013. 2012 is sort of the beginning of the construction part. You could see it was a kind of a mock Eichler. We did a pretty much a gut remodel down to studs. Not huge footprint addition, in fact, none, but lots of interior reconfiguring and sort of glazing changes. It was a dark, kind of gloomy hole, and we transformed it into something quite light and I think attractive. And in this slide, you can really see pretty much the whole HVAC. for this project. So remember, this is this mini split, wall mounted mini split, just under 2,000 square foot home, heated and cooled with just that single split unit. Ventilation supply all through these two nozzles into the plenum living space. And this is an image you could see we did still have a gas cooktop in this, and the only reason we put it in was because the clients had already bought it. So they already had the gas cooktop before we got to them. And they also had a gas water heater, which we reinstalled because it was still in good shape, with the caveat and the understanding that would be replaced at the end of life with a heat pump water heater. And I understand it has already been replaced. And finally, I'm going to catch up with the third project in Sunnyvale. So a lot of you have probably seen a lot about the Sunnyvale project. Very simple floor plan, again, 3-bedroom, just under 1,500 square foot, not a big house, but we did, vaulted ceilings to make the space feel big, a great room, living room, open plan. Now look again, this is the return duct up here in this attic space. And here are my supply ventilations. There's a couple of those all marching along this wall. And behind this sort of spine wall are all the living spaces. And above here is the attic. So soft, regular ceiling height in the bedroom and bathroom spaces, and vaulted in the living space. And in terms of the HVAC layout, again, Alan sort of went and did use the same tricks that he'd figured out in Alamo, integrating the HRV and heat pump ducting to really simplify the mechanical system distribution layout. And you can see again in the duct plan, this was the vaulted spaces on here, the living room spaces. Our HVAC is sitting in the attic above the bedroom spaces here. And 8 supply registers, very even, again, balanced layout. And you can see jump ducts, making sure that the air pressure balance across these rooms is also kept balanced, and that the transfer to this living space plenum area can be effective and happen. Again, lots of great data from this project, really confirming all the things that Jessica has spoken about that Passive House delivers. Almost effectively no peak loads. Winter use for this house was radically lower than the average home in the same zip code, which, by the way, was a stock plan. The entire neighborhood was all built pretty much to the same 2-bed, 1-bath stock plan back in the 40s. So the comparison that I was able to obtain from PG&E was pretty effective. But in terms of the actual energy use, my PHPP predicted a little bit higher than what we actually measured. And in terms of winter peak use, 4.3 times less than the average home in that neighborhood. Again, supporting what Jessica mentioned in the definition of net zero, which has lots of fuzzy opportunities to be interpreted creatively, shall we say. This home we were able to find, because it's in such a moderate temperate climate, we could pretty much supply all the solar, the generation on site, even in the more challenging winter months. You can see December, November, January, February. The gray is the EV, the orange is the house. So we are more than adequately covering the total use with the generation, and almost almost throughout the year, but not. So now that I've told you what I really, really want, like the Spice Girls, I'm going to show you that passive house in California is still an absolute no-brainer. It crushes the heating and cooling loads in all the climate zones that matter. This is a quick study that Steve Mann did for PHN for a report that the CPUC is coming out with, showing what the actual reductions are for passive house compared to current Title 24. This was the 2019 Title 24, but the 2022 Title 24 did not make massive strides in those reductions. It sort of added EV charging and a few other measures more than pushing down efficiency. Part of this other CPUC report confirmed that my 2 passive house projects, which I presented on here, I was able to supply hourly monitoring data to them for over a 2-year period for both of these projects, which was then converted into a comparison between 5 Z&E homes in California in similar climate zones. So a pretty close comparison between passive house and not Title 24, but better than Title 24, so Z&E. And what these researchers found was that really the big aha for me on this was that passive houses have no summer peaks. And in a hot climate like California, that is meaningful because when we have our brownouts in California, it's in the summer when they turn off the utilities because it can't meet the air conditioning loads. Winter, there was definitely an improvement, a shift of the peak ramp-up rate of when passive house started to kick in. But in terms of winter, not significant ramp-ups compared to the Z&E homes, which were clearly doing a pretty decent job of keeping winter loads low.
I'm going to show you a little bit my own home. I'm a passive house architect, been doing all electric passive house projects since 2008. So I'm going to tell you a little bit about the why, how, what, and where, with the example of my Passive House Plus project. Motivation. Why would anybody decide to do this beyond the reasons that we've already heard about today that are societal? For us as a family, it was really important that we do our part on climate change. So we didn't want to be a part of the problem. Comfort, huge. We live in Minnesota. We have very cold winters here, and code compliant construction does not provide a lot of comfort. It's drafty. We have radiant heat loss. So we wanted out of that. And also resiliency. We have, changing climate, more severe weather events. So we wanted to be in a building that can weather the storm, so to speak. And the passive house is a great approach for that. So we decided to build Minneapolis's first Passive House Plus, and I'm going to run you through how that all went. So why did we decide to electrify everything? Well, it's climate neutral, so that answered our first request. It's also a universal fuel, so it's something that we need for everything. So it's easy to go to electricity because you can power just about any device these days off of it. We can make it on site. We have solar on the roof, which I'll show you in a minute. We can also build a backup and our storage solution around it. The heat pump efficiency was of interest to us. So the mechanical systems, as Bronwyn pointed out, there's efficiency here to be had. We eliminated all combustion from the home. There's a reduced fire risk, and we have better indoor air quality for it. we didn't have to pay for gas, plumbing, and infrastructure. So that's not even in the building at all. And for me as a geek, there's a simple math here to track my consumption and generation. It's all kilowatt hours. And that's another good reason to go with electricity. So a quick picture of our context here. So we did a tear down rebuild in Northeast Minneapolis, US climate zone 6, very cold, 8,000 heating degree days, our design temperature -31°C or -24°F. So my main concern here is heating, although we do have a cooling load just as well. This is what the house looks like for those who haven't seen that in prior presentation. The passive house envelope, somebody already asked in the chat, how is that different from code building in Minnesota? Well, you can anticipate about 2 to 3 times code levels of insulation. Air tightness, I didn't list that here specifically, is about 5 times tighter. So 0.6 air changes instead of 3.0. And our windows also perform about 3 times better than what code stipulates we have to have. So all in about a 2 to 3 time improvement. Just another impression here. We have active shading on the building, which is important for comfort and the control of the solar heat gains. You're looking at the south facade there on the right-hand side. Passive House Plus, as I talked about earlier. So that means we have renewable energy in the mix, and we did track the PER values. Won't do a deep dive here on that today. Hopefully we'll have another presentation someday where we can expand on some of these subjects. But you can see our solar facade here. So this is really the heater for the home. 60% of the heat load is being covered by passive solar heat gains that come in through these windows. Here's a winter impression. So 3 months of the year, it'll look something like that. And it works fantastic in this environment here. The solar system is located on the roof. It's a low tilt setup, just ballasted system up there. We have 38 modules, 12 kilowatt peak system, and it produces about 12,000 kilowatt hours per year. You can see all the gadgets and gobbins that go with a system like that. And again, the opportunity here is we can do direct consumption. So in an all-electric setup, we can take the power from the roof and directly consume it in the building. Just a couple of impressions of the infrastructure. One thing that changes in this scenario is that we have the main service coming into the garage, and then the house has a sub panel off of that. I'll talk more about why we did that. We also monitor this, and that's important because I wanted to bring you some numbers today. So we look at temperature, humidity, weather, indoor air quality. The whole thing is basically instrumented, and you don't have to do that, but for somebody in my profession, that makes sense because we can learn from that. And here's just some imagery that shows some of the equipment that we use for that. So with that, I generate a lot of data, and that's something I can bring to you today as well. One thing that this graph on the right doesn't show, I should have clicked on the yearly view, is that hill valley problem that Jessica talked about. That still exists in a passive house. So we also have that daily offset of when electricity becomes available on the roof versus when it's consumed. And then also the seasonal load shifting, where in the winter months we produce the least off the roof, but we still have some of the highest consumption in the building due to the heat load. So just note that as an ongoing challenge. So let's talk about the process real quick. What are the things that we did to be able to do an all-electric passive house? So the first thing is we rotated the building on our block 90 degrees from the building that was there to make the broadside face south. That makes the building a passive solar collector. That's a really important part of the strategy. Secondly, we made it a certified passive house. So the construction methodology, the R values, air tightness are all at the passive house level. This brings the peak heat loads and the overall demand down and enables the all-electric fueling of the building. The next thing we did is we basically erected the back of the garage first. And as soon as humanly possible, we put the electric service in, subscribed to wind power, and we effectively built the entire building off of wind energy right out of the gates, trying to avoid any kind of generator or polluting equipment in the use of even the construction. This also extended to our construction methodologies, but again, I won't be able to do a deep dive on that today. With the demo of the old house, we removed the gas service. You can see the remnants of it right here. That was a bit of an upset for the gas company because they can't imagine a building without a gas connection in Minneapolis, Minnesota. And they also had no protocol of removing the service, which means that that thing just got abandoned on my site. So somebody cut through it with that shovel, and so the remnants of that are buried somewhere in my front yard, and that's where that story ends. Then we went for solar. We installed that within the first year on our roof, and with that, we were able to go essentially all electric, and then install a bunch of heat pumps. You don't have to read these slides here. I'll give you some pictures. So one of the benefits of going all electric is we can leverage this technology, which isn't particularly new, really, if you think about it. In refrigerators, we've had it for decades. And so in my home, you find it in the refrigeration, you find it in the dryer, you find it in the heating and cooling system. That's house and garage. We keep our garage frost-free. You find it in the hot water heater that you can see there on the right-hand side in that picture. And then also find it in the vehicles these days. They are also efficiently heated and cooled with a heat pump. And the reason why we use heat pumps is it's a tried and true technology. It's been around the block. It is very reliable, at least in my experience. I've used these in projects since 2008. They don't quit. They work really well. So they run through the cold periods of the year. There's a lot of myth around that they turn off at some temperature. That is simply not true. And they always run at an efficiency better than one, meaning they always beat direct electric heat. So there is a benefit to putting them in over electric strip heating or in-floor heating or something like that. Also, modern heat pumps are very good at adjusting to varying loads. This goes back to where Bronwyn left off. Our trades are not very well trained, so sizing of equipment and even availability of small equipment is not great. So sometimes we have to work with what we can get. But the benefit here is that with the variable compressors and fans in these units, they can adjust really well to the loads that shift over the course of the year. Also, load shifting is an option. If you do a multifamily building, you can take your cooling load and make hot water with it, for instance. Or a simple example in my house here, the hot water heater, as it sits in my mudroom, will do some cooling and dehumidification for the whole house. And that's essentially a freebie that I get out of it by virtue of making hot water. And then I already mentioned it is universally available for all these different opportunities and devices. All right. What's a little bit difficult about them is if you want to monitor them, how do you get to what do they actually consume? Again, won't do a deep dive today, but I'm working with a PHI on the analysis of my house. We just started that process here, but one of the things we ran into is I have one outdoor unit that supplies both the garage and the home. And to be able to take that apart and see what energy is consumed where is somewhat tricky. And then, of course, I have a hot water heat pump inside the home that uses warm air from the house to make hot water. So we have another heat pump sucking on the first heat pump. And you can imagine, dividing that is somewhat of a challenge. So just know that if you want to monitor that and be specific about it, that does take a little bit of work. And in the PHPP, for those of you who are passive house practitioners, that's also still a bit challenging to model. So let's get into some of the data just to show you how this all works. I built the house in 2020 or finished it in 2020. So we've been in it about 4 years now. I have 3 years worth of data that are relevant and good. And you can see that here. So the short of it is that for the most part, what I do in the house and the garage, we're at an annual net zero. That doesn't mean we're net zero on any given day. We also see that, fluctuate a little bit. So this is something that we've learned, but generally it works as we had intended. We can cover some of our electric driving also from the roof, but not all of it. And we can talk about that more. Cost is something we always get asked about. Cost is relative, right? The cost of a kilowatt hour of electricity is different in different places, and net metering works differently. But for us specifically, on the right-hand side of that column, I'm showing you what that is. In the first year, we ended up paying $73. In the second year, we made $266, and in the third, we made $424 that year. So I effectively do not have a utility bill at this point. And I should note that includes all the electricity or all the energy consumed on my site. There is no cop-out, there is no other system here. And all of the energy that's consumed is either off my roof or solar power. And then last year, my electricity company switched the contract to solar and wind power. combined. So NERS makes no difference. It's a climate neutral site. Here you can see an analysis of what we measured and where the consumers are. So one of the big changes, of course, is that cooling and heating the house is no longer the biggest load. If I showed another graph of a standard home in Minnesota, you would see the heating and cooling basically eat the entire pie. That is simply no longer the case. The EVs have risen to the top, and we don't even drive a lot because we don't have a commute. My wife and I work from home. But even at that, you know, the EVs are the biggest consumers now on site, hence our different wiring. I showed it earlier. So we wired the main service to the garage. Right there, the EVs plug in. That's where the biggest consumer and ad hoc load is. And then the house is merely a sub panel off of that. Also, a quick thing to note, we keep our garage frost free at 50 degrees Fahrenheit during the winter for practical reasons. And the energy that's consumed there is also not something to forget. That's 11% of our entire pie. So that rivals the house. The garage is built almost like a passive house, but what comes to roost here is certainly the garage door, which is never at the same quality as a passive house window, can't be sealed as tightly, and of course is open and closed many times a day, and therefore there's heat loss there. Here's a quick graph, again, based off the measured numbers of how the loads in the home lay out. So we're just starting to dig into this in comparison to what the PHPP told us was going to be consumed. And the good news here is it's very close. So we see that the heating and cooling of the home and hot water, some of the bigger consumers here are right in line with what was predicted. We also see that some stuff is different. You know, for instance, now that we work from home, we run a commercial grade network in the home and a little server. And so we have a significant amount of load there for networking equipment that, you know, the average consumer may not have in their house. Another thing that we've learned from our house is that the peak loads are really manageable. That was already being alluded to earlier. So I did a quick calc here because we're in the process of looking at a battery backup. So our critical loads typically amount to only 6,500 watts, and that includes basically full heating and cooling of the house happening. So we wouldn't have to scale back on anything. We could continue to go through an outage at that load with hot water and heating and cooling still going, which again, the passive house can coast for a while, is maybe not even necessary. And also our base load is fairly low. So both of those loads very well managed by the house being such a low consumer. So considerations based off that, you know, the electrical loads and electricity demand in a passive house is very different than in conventional buildings. Heating and cooling are no longer the biggest loads, perhaps not even the biggest demand over the course of the year. The vehicle charging is becoming the new peak load, at least in a single family home setting, if that's how you do your transport. And so for us going forward, we're also looking at that uninterrupted power supply. And that's also in anticipation of time of use billing that our state is probably going to get it within the next 3 years, and then our solar rewards will run out. So we want to make sure that we have more resilience and then cash flow optimizations. And in an all electric building, it's perfect. You're already set up for that. So the technology plugging in a battery backup system becomes possible and relatively simple to do. Here you can see some of my monitoring just for an impression on that and what a battery backup solution could look like. You know, you have the storage and then the inverter. So with that, let's talk about some of the challenges real quick that we still have. And I'll give you here a picture of my solar panels covered in the dead of winter. That is a challenge, obviously. So if we're using the on-site generation as part of the big picture, we got to deal with this, right? So part of the year, my panels will be snow covered. So in that case, solar is zero. Do I have a power outage? Then solar is also zero because they take that system down because you can't put anything on the grid. Also, a cold winter day like this, maybe without the snow, you know, I get 15 kilowatt hours per day off the roof. On a summer day, I get 85 kilowatt hours off the roof. So again, this is just an illustration of what Jessica in particular talked about earlier. But you know, the gas disconnect I talked about, the company wasn't really prepared for that. That didn't create any problems, but it is maybe a challenge because I got a bunch of stupid questions from them that wasted my time. Grid regulation is a challenge a little bit. So my power company was trying to tell me how many solar panels I can put up and how that all works. That's not always what you want in a design. So you got to work with them through that, especially in new construction here in Minnesota, that can be a little bit challenging. So the PV system size, the system setup, the batteries, the rewards programs can all sort of reach into your design ideas and targets. So just know that as a challenge when you go all electric that you might have to deal with. Another challenge is our gas here is way too cheap. That might be true in other parts of the country, but it certainly is in Minnesota. So if I compare myself with another home at a similar size that is a conventional building with a gas furnace and electric service, you know, if you just look at dollars a month, now I don't pay that because I have renewable production, but if I were to pay outright, you know, I might pay the same money that they pay, even though my home is much, much more efficient and uses a lot less energy. And that's just because these prices are manipulated and do not cover certainly the environmental damages associated with it. And so anyway, that's a tough competition. As I mentioned, my family's motives were not predominantly financial. And in our market, it doesn't work if that's the only thing that gets you up in the morning for a passive house. One other challenge, we need more flexibility from the manufacturers on the heat pumps in particular, but we also need smaller equipment. We need equipment that could do multiple jobs at the same time. And we need more transparency from those vendors. They need to tell us the efficiencies in a universal way that we can plug into the PHPP so we don't have to simulate every heat pump individually. Some of the successes real quick here. So here's a new project that's just about to wrap up that I worked on. You know, the electrification just works with passive house, at least in our climate zone here. You don't need any cop outs. We don't need a fireplace. We don't need a gas hookup that we're hiding somewhere. It's all electric. You can see that here on the right-hand side. There's the little hookup coming into that house. All loads are accounted for, and we're doing it again and again in our extreme climate zones. My home has been just about net zero since move-in, but not on any given day. Just know that too. For that, we would have to do something with batteries and or the grid. Even some EV charging we can squeeze in from the roof. The all-electric passive house is super easy to live with, but it's still affected by power outages. So again, you know, we would have to have some kind of a backup for that. Low consumption and incentive programs mean zero energy bill for us. And we have that small surplus every year that helps chip away at the original cost of our PV system. It'll cover about a third of the system cost over 10 years. That's the runtime of the program. And then as I showed, you know, passive house puts a cap on peak loads. It's much more compatible with the grid capacity than business as usual. All right, and then maybe last year, the opportunities, some of the things that I'm working on and I've encountered. You know, if we go all electric, we can do different kind of wiring. I showed you how the panels are laid out differently, perhaps in my house and in my designs, and they are in different locations. We're also getting into DC wiring, not just AC. So if we have DC production on the roof, for instance, we can take that right off and do it, you know, connect a vehicle charger, for instance, to that. Also with on-site storage, you know, that there are DC systems and AC coupled systems. Can't do a deep dive on that, but those are opportunities. We get to get into the sort of RV and off-grid realm much more once we're all electric. And then maybe last but not least, the on-site production and storage will shape the economics entirely of a passive house that is all electric, you know, in a time of use scenario. And when we have some storage and production on the roof, you know, we can get to no utility cost and or revenue. So that's a completely new way of looking at your utility bill like that. So with that, hopefully I made up a little bit of time. I thank you so much. And I look forward to doing a deeper dive on my house with a PHI and maybe one day being able to present that to you. Thank you so much.
I was intrigued, Bronwyn, you showing in your graph there that the renewable production was covering not just the home, but the car usage as well. And Tim, you spoke to in your context with that. I don't know if I've seen the car usage come up in the PHI literature. And also in terms of a battery as a storage item with the house. And I thought from each of your contexts, if maybe we could just take a minute to dive into the synergies we're seeing or the possible synergies with our automobiles. Bronwyn, why don't we start with your house where you're showing getting the EV for free?
Sure. I've seen the Alamo house. We got the EV charge for free. The Sunnyvale 2 house, EV charge for free. The Sunnyvale 1 house had no solar because the entire roof was shaded by the redwood trees on the site. So, it's great for people who have solar. It kind of raises a lot of complicated questions. The first of which is like, I'm kind of a cyclist myself, not a car fan, but I have clients who drive cars, and I have a client who drives a lot of cars. So accommodating them and being realistic about, the American context, Passive House allows that and actually, supports it in a kind of maybe a codependent kind of way. But it's a single family. There's lots of things to unpack there, like including, the American West is littered with single family homes. So, we are in the West, it's 75% of our land use is single family homes, or, residential. So, it's complicated. I don't know what Tim thinks, or just, the European perspective is very different. So
yes and no. I mean, they
American.
drive cars too, right? So I have friends in Germany who live in a passive house and have an EV similar to what I do, and some of them drive way more than I do. So I don't know. I mean,
So what do
I
you
look
see,
at
Tim,
the
with your
opportunities. Sorry, Ken. Go ahead.
Yeah, no, go. What do you see with your
Yeah, I
usage?
look at the opportunities. I mean, first and foremost, for me, the connection from the EV is maybe less with the passive house and more with the solar panels on the roof. Not that you said something different. And as somebody who works from home, I have the benefit that I can charge the vehicles when the surplus is available. So it's probably more realistic to say for my property that the surplus, goes into the car batteries, and the house doesn't really benefit from that. Jessica talked about that at length already, how the curves of the home really don't match a solar curve very well. But with the car, you can get closer to it. So I can fuel my cars for free, and then say, okay, in the winter I buy grid electricity to heat my passive house, and that's maybe more accurate. I think the opportunities are, with bidirectional loads. Some manufacturers are teasing that. Others have already come out with some version of that, but there's no standard yet, which is a challenge. But there is, of course, the opportunity to play that game forwards and backwards. So if you look at that, the cost of a vehicle today with a significant battery is much cheaper than buying the batteries outright. So in other words, you can have a battery with 4 wheels for less money than a home battery. And if it can go bidirectional, you can use that to pump energy into it and then suck it back into the house. So I look at that as an opportunity. I don't have that yet. And also it's somewhat counterproductive perhaps, because in a real emergency, if you then really need the vehicle, you have to make that choice, right? Do I fuel my home with it, or do I flee, or whatever I need to do, in my car? So that's something also to be discovered, I think, in the future. I think there's cool stuff coming online with that. We'll see where that all lands. I'm looking at a stationary battery addition to my home, just because we get regular power outages in our neighborhood. Most of them are probably weather driven, not brownouts like you might see in California, but it's still an annoyance. And for me, the annoyance is not, I think I saw that in the comments, the passive house is, again, a thermal battery, so that can coast for a day, days, whatever. I don't really care. I could always put on a jacket, and I know it'll never be freezing in this house. But it's more, when we're working from home, that interruption that, you're in the middle of a Zoom call and poof, there it all goes. And that's an annoyance that I want to get away from. So I think these are the short-term opportunity is some kind of a battery backup. Long term, we need to scale that. And of course, the grid needs to do the same thing to get us a buffer so that we can have the renewable in the winter when we need it.
Right. Great. Thank you, Tim. Jessica, any thoughts on EV? And also maybe touch on, I mean, everybody is very very jealous of the combo units, the magic box, and
Yeah.
you know, does that bring material? Do we see that in optimization benefit having that combo box, or is it more a space saver?
Bit of both. I'm going to start with EVs, if that's okay, and then switch over to the compact units. Both interesting topics. EVs is a bit unexpected, but a good one that you're touching on it, because I think it's a really important part. If we step back and talk about the whole electrification, and it's not just about buildings, right? Electrification touches many parts of our lives, and buildings and EVs, cars, like transport, is a big part of it. I like the approach that you guys took in terms of let's think about the opportunities, and definitely using EVs in terms of battery storage is, I think, a good idea, and development's happening there. It's going to help with the short-term thing. It's going to help a little bit, but it won't address that big challenge, that big elephant that we've all been speaking about in terms of, you know, the hill valley that you referred to as, Tim, with the seasonal thing. So it doesn't, right? It doesn't. Yeah, it helps with the short-term storage, but not the fundamental problem that the buildings can help with. Plus, I think one benefit is if we manage to really bring down the demand for buildings, as we do with the passive house, and Tim and Bronwyn, you both showed some data, which is fantastic, because that really makes it tangible and proves that it works. And obviously, then if we free all of that energy or electricity by not needing it for the buildings, it becomes available for other uses, such as, for example, the transport sector, which also needs to move towards electrification. So I think it is important in the bigger scheme of things to look at both. It makes it even more urgent if we talk about energy and electricity savings, because it's not only the buildings that we're electrifying, it is that massive block of electrification. So all of these things that we're talking about, all of this bringing down peak loads, bringing down demand, becomes even more important and even more urgent when we look at the bigger picture, and the transport is also a big part of this story.
Yeah, fantastic. Well said. And I think we'll leave it there.
What's interesting about passive house and electrification is it really works at every scale. In some ways, it works better with big buildings because it's easier to, you know, the amount of energy per square foot used for sort of a larger, deeper building is, it's an easier challenge to meet because of the larger sort of volume, the relationship between the volume and the perimeter. But I'm going to talk about my journey with Hotel Marcel, which was my first passive house project, although I've been sort of feeding off the energy of the passive house movement over the last decade or so, and had a chance, as some of you know, to go to Austria to present this project, and I'm just so impressed by the amount of enthusiasm and creativity and innovation. It's really a dynamic area. So anyhow, the story of Hotel Marcel sort of comes from the origin is, you know, we have to stop burning fossil fuels. You've talked about that's you know, the two big sources of climate damaging emissions are the transportation sector and then the buildings, which those of us in the design field are responsible for. So I've been committed to not burning fossil fuels, both for my transportation, but even for my own home, which I electrified about 6 years ago. And so everything I learned in my home, which wasn't passive house, but you know, we did a deep energy retrofit, but I realized, gee, this is a much better way. It's cleaner, safer, healthier, more economical. So when I got obsessed with this building, which was designed by Marcel Breuer, someone who I'd long admired, sort of the very influential Bauhaus trained or Bauhaus teacher who made furniture and then modern buildings in America and trained a whole generation of sort of architectural heroes, from Paul Rudolph to I.M. Pei to John Johansson. I mean, the list goes on and on. Philip Johnson, the whole Harvard Five that came down to New Canaan, which is where I grew up. So I sort of grew up in the shadow of these mid-century modern architects. And yet this building, designed by the leader of that group, Marcel Breuer, was sitting abandoned in New Haven at the edge of the highway for 20 years. So I decided to sort of fashion a plan to turn it into a hotel. And now it's Hotel Marcel. And it's the first Passive House certified hotel in the United States. And as I understand it, the largest Passive House certified hotel in the world. So it's a great case study to look at in terms of how we can scale up these principles that were talked about in the first section. So the program for the building, just to have it function as a hotel, the first four things we had to do was design something that would help pay the mortgage. We were able to fit 165 nice guest rooms in, over 7,000 square feet of meeting space. In order to make the numbers work, we listed it on the National Register so we could access historic tax credits and navigate the approval process with the National Park Service and the SHPO, State Historic Preservation Office, for that. But that was really important because that covered about a third of the hard and soft costs. And then in order to be financeable, we had to meet hotel standards for a major brand, and we have been delighted to work with Hilton and the hotel as a boutique hotel as part of the Tapestry collection. But on top of that, just given my background as an architect, developer, owner, I figured this is an opportunity to sort of go beyond what I did for my own house, which was to pursue LEED Platinum certification, which we had done for the last 2 apartment buildings that we had developed, and then to shoot for the Passive House certification, which you'll be hearing a little bit more from Dylan, who we worked with closely on that. But that in some ways was the easiest thing we did in terms of the number of things we had to focus on, and we'll talk about that. But we also committed not to use any fossil fuels, which actually is it became sort of the easiest thing to do, but it's a thing that no one else has done with hotels in the United States. And so there's a real fascination with it, as all the big hotel companies have pledged to reduce their fossil fuel emissions. And so we're the first real prototype that people can come and see, kick the tires and say, yeah, you can have a all-electric hotel that doesn't use fossil fuels and still outperform the market and get great, rave reviews on Google and whatnot. But we also had a goal of making all the energy on site. Originally, we had the ability to add more solar canopies, which were scaled back, and we're not quite meeting where our model was. So it's a goal that we're still pursuing, but haven't met yet. But obviously, it's a lot more efficient, and it saves a lot of money if you don't have to have a utility bill. And we do have one, but it's about a third of what it would be with a normal hotel. And then we do all kinds of other things in addition to Passive House to reduce energy use. We have a power over Ethernet system for all our lighting and shades that reduces our lighting and shade energy by about 30%. And we have a microgrid with 1.5 megawatt hours of battery storage, which actually helps us a great deal in shedding load and avoiding any kind of demand charges. Of course, the Passive House design gives us a very consistent load throughout the year too. But in most commercial buildings, half their electric bill is demand charges, and we're able to eliminate that. And then we can also operate off-grid if there's a regional power outage, which has happened 3 times since we opened. So that's a great thing. We don't have to buy a gas generator. So again, here's our certifications for these achievements. Of course, as an existing building, we met the EnerPHit standard for PHI. Since this is a Passive House sponsored event, I think I'm not going to go into too many details about what that means, but these are all things with a commercial building that you have to take care to do anyhow. And I don't think that there's that much of a premium for it. It really just requires more attention to detail, particularly with the insulation and looking out for thermal bridges and doing air sealing. This building actually really worked very well. It's a very tight building because it's made, the whole exterior is made with 6,000 PSI concrete. So it's a very tight building. And then we had to get some special windows made, which actually, the windows cost $1,000 each instead of $500. So there was a premium there, but people love the quiet of those windows. I don't think we talk enough about how important it is for people to just be able to experience quiet in their lives. And these are the quietest hotel rooms that our guests have ever stayed in. They repeatedly tell us that. So that's a real benefit for a hotel and probably any building, just you suddenly have a very quiet environment. And then we have, of course, fresh air ventilation with heat recovery. We've got 2 big Swagon gold ERVs up on our top floor with continuous filtered air, which really came in handy when we had all that smoke coming down from Canada. We had the freshest air in the county inside Hotel Marcel. We'll talk about LEED Platinum, but I think it's a great set of measures to make sure that you're being sensitive to a whole range of environmental issues and sustainability issues. And there was certainly no conflict between our doing this and meeting the Passive House standards. So again, our solution to address this dire climate crisis we're in is to reduce our energy requirements as much as possible. Passive House is really the primary way to do that. Obviously, recycling the whole building that exists eliminates almost all the upfront carbon for a commercial building. So that may actually be the single most environmentally sustainable thing that we've done is reuse this amazing building. And then there are all kinds of sort of smaller challenges we use to reduce our energy use. A lot of it relies on heat pumps, but also control systems and programming. And then we have electric systems that other hotels just haven't tried before. We have an all-electric kitchen with induction ranges. We have an all-electric laundry. We actually just recently replaced our energy hogs, which were these resistance electric dryers with heat pump dryers. We have the first air source heat pump made for commercial buildings by Mitsubishi for domestic hot water, what they call the Heat 2.0. And then we also have electrified our transportation system. We have an electric shuttle bus. We have 24 car chargers, and then we try to make the power on site. So here's some photographs. I encourage everyone who to come visit, because you can't really appreciate it fully without spending the night in the hotel and enjoying the fresh air and the quiet Calm. But we have a lot of wonderful public areas, and there've been a lot of industry events here already with particularly with the green building industry, but also pretty much the whole cross-section of commerce and nonprofits in the New Haven region. We work with Dutch East Design, a Brooklyn firm, on the interior design. And I think people are remarking that, gee, this is the most energy efficient hotel, but it's also one of the most beautiful hotels. So sometimes there's a perception that when you have an energy efficient building that there's some compromise in comfort, or you might put a sweater on, or it's going to be not quite as enjoyable. But I think it's the opposite. It's consistent temperature everywhere. In the room, we have the Mitsubishi VRFs right inside the door, which reduces the amount of ductwork we have. But it's exact same temperature right at the window as it is when you enter. And so there's a whole range of different types of hotel rooms. And then here are some of our meeting areas. We took the top floor, which was previously a windowless mechanical floor, and turned it into a meeting room floor with guest rooms. And we have an outdoor courtyard as well for gatherings. And we put these windows in on the 9th floor. You can see in the bottom right-hand corner, those are Passive House windows. They're 2 big sliding windows. And so we've suddenly brought a lot more natural light into that floor than existed. So we cleaned the building. Here you see the cross section. It's a remarkable building because it's sort of missing the 3rd and 4th floors rather, which actually creates a little more perimeter to insulate. But the facade was really well suited because all the windows are inset about 30 inches. So we get this great passive shading in the summer and the solar gain in the winter when it's helpful. Here you can see the the beautiful precast panels, which provide that passive design. And we work closely with Dylan's group, Stephen Winter's associates, to come up with a plan for insulating on the inside of the building. They did a lot of modeling for us, and we came up with, a system of closed cell foam and open cell foam, even using some air gel insulation and tape to create a passive house compliant building envelope. And then we have windows that we bought from a company called Klar, K-L-A-R, that were made in Poland with really high performance glass. And these are a great investment because they really do a good job with the building envelope. As I mentioned, all of the heat pumps are in that space, the vestibule as you come in, the door to the hotel room, adjacent to the bathrooms in the ceiling. And these are ducted from the fresh air that's filtered in the ERVs up on the 9th floor. And then here you see a screenshot of what we are achieving with the Swagon the Swagon ERV, the energy recovery ventilator, where you can have outdoor air at 34 degrees. And just by passing through this heat recovery wheel, it's increased, the temperature goes up to 52 degrees. So the heat pumps in the rooms don't really have to work nearly as hard. So that's a big part of our energy efficiency. And we also use the power over Ethernet system, which Sinclair Digital in Fort Worth helped us design and install. So we have actually more convenient touch screens, so you can set your thermostat. There's sort of preset lighting scenes and control your temperature, all with the touch screen as you enter. And then there's also some buttons at the bedside for lighting and shade control. Here are the Mitsubishi Heat 2.0 heat pumps, which look like the other outdoor condensers. And then we have 2 hot water plants. We've never had a single issue with them. They work beautifully. And I think economically, they are less costly to operate than, a gas hot water heater. But these didn't exist. We got the first ones in the country, and now they're being put in everywhere. This is sort of a glimpse at our power over Ethernet system. We actually recycled the office lights. They now are in some of the guest rooms as well as in the hallways. And all of the lighting and shades are controlled with a Cat5 network that can be remotely programmed. And here's our all-electric kitchen. Chef Megan does a great job. She tells us that she can make things faster and more efficiently. It's easier to clean stuff. We're able to use a recirc hood, which saves energy because we don't have to condition as much air. So the all-electric kitchen is it's sort of a new thing, but people are starting to replicate it already. And here's our laundry with the initial resistance electric dryers we had. Those 2 dryers in the back actually used 126 kilowatts each when they were running. And so when they were both running, they used more than the base load of the building. So we couldn't get initially when we opened the hotel heat pump dryers, but earlier this year, we were able to bring in these Electrolux commercial heat pump dryers from Sweden. Now they're available in the US. And these only use 6.5 kilowatts each. So we've reduced what was our major energy use in the building, drying linens, from sort of a peak of basically 250 kilowatts down to about, we have 6 of these, so it's about 40 and change, and they work faster and better. One thing we did that was sort of innovative is the room, because these are not ducted, we put a air source heat pump hot water heater in the corner of the laundry room because the room was getting a little hot from the heat pump dryers. Originally, the dryer sat in an outdoor plenum, but by putting this here, we're able to cool the laundry room and also make the hot water for the washing machines with the same energy, just moving it from one place to the other. So we're continuing to innovate and use the hotel as a laboratory. We're even making our own cleaning chemicals now with this new system instead of having to buy all the chemicals and have them shipped in plastic bottles. and we're looking for other things. We're also looking to try to add more solar. We're looking at maybe even a wind turbine, because right now, we're only producing about a third of the energy, and our goal is to produce 100%. We have a microgrid controller by Agito, so we can log in and see where our energy is going at any point in time. This is one of 2 battery rooms that we have in the building. We actually just added another 2 racks, and this is a screenshot before we replaced the dryers, and you can see the spikes in the orange line when the dryers were on, which we've now eliminated. So we look at this, and this is a day in the summer where we were making more energy than we were using, but this is an atypical day. Can tell me if I'm almost done, but if I've used up my time, I can go even faster.
You've got a couple minutes.
Okay, good. So we were talking about electrification. This is a vehicles, and that's a subject close to my heart. I'm the chairman of the EV Club of Connecticut, and so we're working hard to spread the word about how EVs do for basically cars what Passive House does for buildings, in terms of just being more efficient and making the transition to all electric more feasible. So we have 12 Tesla superchargers. We also have 12 level 2 chargers for overnight guests, and that brings in a little more business, and it's also a revenue source for us. We also have an all-electric van that was converted by Maxwell Vehicles, so that we can pick up people at the train station or drop them off at Yale or at the hospital, whatever, without burning any fossil fuels. And I mean, these are all very easily replicable strategies for hotels. And then we also we're always trying to layer on things. I think the solution is actually to have fewer vehicles. So we actually now have bikes, and we're going to get some e-bikes for our guests to use. But this sort of shows how we are performing relative to other hotels. There's actually a really good database that New York City has done, because they are collecting the data based on actual bills. So you can see that hotels are really the worst performing building type in New York City, with energy, EUIs of averaging 112. Now this was our modeled energy at 43. I think it's actually 42 right now. So we're right where our model is, but I think we can do better than that. So we're continuing to work on it. And then, of course, carbon emissions are the big thing. And in New York City and other places like Boston, these fines are being imposed if you're over a cap that's set. And if you have zero emissions, you're not going to have to worry about that. But so this is, we're sort of proud that we've come up with a model that's replicable, that other hotels can follow. And there are a lot of hotel companies that are desperate to do this. All the major hotel companies have pledged to reduce their emissions in fossil fuels by 2030. Little known secret is they're measuring them, but they're actually going up. So I think you're going to suddenly see a realization that if they just do what they've been doing without incentivizing or penalizing folks that are using fossil fuels, I think that there's going to be a pretty radical change soon. And then the other thing I sometimes talk to folks about is, what does this do in terms of our fossil fuel emissions? There's Cornell has a database of all the hotels in the world, and you can look at what is typical in terms of fossil fuel emissions. And if we had built this as a conventional hotel in Connecticut, the hotel would be producing 715 metric tons of carbon pollution every year. And then if you go to the EPA's website, you can put that in and it'll give you what the equivalents are. The most striking thing for me is that is the amount of carbon that you would need 846 acres of US mature forest to absorb every year. So if you build a new hotel conventionally, it has the same effect on our climate crisis as clear cutting over a square mile of mature forest. And I think there's this perception that you can buy some offsets or plant a few trees and all's good. But I think I've realized this really requires sort of a radical change in direction for everyone if we don't want to have these days getting hotter and hotter. So that's my presentation, Ken. I'm available to answer questions, but I know that Dylan in particular can give a lot of the backstory of this because his company did all the modeling together with all the other great things he does. So I'll be available to answer questions later on.
Thank you, Bruce. That's incredible. I mean, it is the most impressive single, like, all electric project I know of, because you've really taken it to another level, and you're taking energy efficiency so seriously with Passive House and in every step of the way of all the technology that you're dealing with. So
the thing that's nice about it is people can come see it and kick the tires, because there are a lot of people who are designing Passive House buildings haven't even stayed in one. And so here you could bring your client, stay in it, you can see it.
I want to get through some of the main points with regards to essentially where we're at with operational data of high performance Passive House buildings, Passive House certified buildings mostly, and then dive into some of the technical challenges with electrification of large buildings, particularly multifamily. So, but let's just dive right in. I want to talk about actual results. So a lot of us, I've seen a lot of great data on some single family homes and some smaller projects. Bruce kind of forayed into the larger scale projects as well here with actual energy use data, which is really exciting. So let's keep that theme going here and look at energy use data of operational Passive House projects in the Northeast climate, which is the region that we work on primarily here at Stephen Winter Associates. So this first graph is, we're diving right into graphs here. So this is the measured peak heating demand. This is in watts per gross square feet of about 15 non-Passive House, or what we call conventional buildings, where we had 15-minute utility data from these projects. They're all multifamily. These are all in New York City as well, big scale projects. And these are all conventional, code minimum, however you want to kind of frame it. And then we have Passive House projects. We have about 6 or so Passive House projects that we have the same granularity of data, 15-minute data. And what we're looking at here is on the horizontal axis, this is the outdoor air temperature, and the vertical axis is the peak heating demand intensity at those outdoor air temperatures, and the bolded lines are the averages of the data set that we have. And you can see, particularly as you get below 50 degrees Fahrenheit and it gets more extreme the colder you get, the slope of that red line, the Passive House line, is extremely flat. In other words, the peak heating demands are barely increasing as it gets down to 20 degrees Fahrenheit, 10 degrees Fahrenheit. That's a huge gap from conventional construction. You can see that graph just slopes right up, and that translates to more of a strain on a grid when we think about electrification of our heating systems. So what we're seeing is Passive House with actual energy use peak heating data. Paul or Mom, I'm gonna steal your words. It smashes the heating loads down, and we're seeing that in reality here. So it's extremely exciting to see that this works not only at small scale, but also at big scale. So we also have some site UI. So this is energy use intensity, or the common metric to look at whole building energy consumption per gross square foot on an annual basis. And you can see we have here about 7 projects, all in New York City, except for one, which is actually the lowest energy user, which is a multifamily senior housing building in New Haven, Connecticut, which is actually a retrofit of an existing historic building. Also, I think went for historic tax credits. So really, really exciting stuff on the retrofit front. All the other buildings are new construction here. But you can see that we kind of are getting results that are showing Passive House buildings with, again, large scale. You can see 272,000 gross square feet, 139,000 gross square feet, 113,000 gross square feet. These are large scale, high rise multifamily buildings are coming in the low to mid 30s for a site UI. And we see sort of a trend building. The couple outliers there, particularly the 50.1, is one that is the smallest building in this data set, but it's also a building that was one of the earlier projects, and it actually had gas heat in it. So we suspect that that is related to some of why the energy use is a little bit higher there. But nonetheless, we see that Passive House is working and really bringing down EUIs especially when you compare this to some benchmarks and some conventional comps that we have, which are the blue bars. So the dark blue bars are multifamily buildings on average, both with vintages before 2003, which has a site UI on average of 85, and post 2003, when there were some more significant energy code updates, of 73. So when you compare the passive house in EUIs in the mid to low 30s compared with those benchmarks, you're seeing about 50% use, 50% reduction in energy use, which is really, really exciting. And the lighter blue bars are actually two buildings that are comps that are code minimum or conventional style construction built around the same time as two of our passive house buildings in this data set by the same developer. So there's a pair of two buildings, one passive house, one of these comps, and then another pair by the same developer, same scale, same density. And you can see those conventional comps are still in that 67 to 73 range. So what we're getting at here is energy use reductions in these passive house buildings upwards of 50%. If you told me that when I started this journey into the passive house world 8 years ago, I would have been extremely excited to hear that. And it's really inspiring to see. Now, these buildings have gas-fired boilers for domestic hot water, which on average, maybe at best, get an annual average COP of 0.95, 0.95. You know, we are entering a world here where electrification, particularly of domestic hot water, is going to start being more common. So what if we had a heat pump for domestic hot water on these buildings? What could we expect? You know, on average, even a conservative estimate of 1.5 for a COP for domestic hot water of this electric system, maybe somewhere between 1.5 and 2 on average. We could see the site UIs in these buildings come down another 10 to 20%, so potentially even get below the 30 range on average. That's exciting. That's real progress, and I think you know, this is something that as we start to get more data, we're really going to continue to learn and continue to grow. But I think we're also going to continue to see results, and that's what we're seeing so far. So how do we actually get there, and how do we do this efficiently? I want to talk about particularly domestic hot water. This is the biggest piece of the pie in multifamily buildings right now with regards to energy consumption. You know, we've solved the space heating problem. Passive House does a really good job at smashing those heating loads down. Space cooling right now, from what we can tell, is not a major load. It's very important, but it's not a major load in these buildings. Domestic hot water is the specific piece of the pie that we really need to focus in on. So I want to highlight some technical challenges, but also solutions and things to think about, and how to help reduce these loads in these large scale buildings. So first, with any domestic hot water discussion, it's helpful to set the stage with regards to a central system versus a decentral system. And by decentral, I'm talking about really in-unit systems. So that's what I'm going to focus on here first. So one, I think, I don't want to call this a misconception, but it's something that I think can get forgotten or not treated with enough sort of consideration. And that's that unitized heat pump water heaters are not the same thing as electric resistance water heaters. You can't just take one of these tanked water heaters and stick them in a closet and expect it to run well. You have to understand that it's a heat pump. It creates cold air and it needs warm air to make, or it needs air to make heat. And the output of that process is cold air. And if you have cold air being dumped into a closet that doesn't have enough free air or enough ventilation air, the heat pump water heater will turn into an electric resistance heater. And I'm not saying this in theory, in practice, we see this happen all the time on operational projects that don't put careful thought and consideration into these design of these heat pump water heaters. So a lot of this I just kind of mentioned. This is a diagram just sort of explaining and showing how these heat pump water heaters work. But really the key question here is, where does this heat come from? And where do we discharge it? The cold air is about 15 to 20 degrees cooler than the air that is sort of it's incoming. That's essentially the amount of change in temperature that these heat pump water heaters create with this air. But it's not just about the air issue. It's also about comfort and noise. So these units have compressors in them. Compressors are loud. You're probably all familiar with a refrigerator, right? That has a compressor in it. It's the same kind of thing. These can be noisy. One actual story that I like to tell is, I believe, a manufacturer, I don't know who it is, I'm not calling anyone out, but there is a heat pump water heater that has an option for what's called quiet mode. And if a resident is annoyed with how noisy it is, they might be inclined to turn on quiet mode. Well, quiet mode is electric resistance. It turns off the compressor. So we have to think about this really thoughtfully. So the way to maximize efficiency in these units is to minimize resistance. So really the key to minimize resistance here is give these heat pump water heaters enough free air volume. They need air to breathe and to not freeze out the space they're working in. So conventionally, in a lot of single family homes, we see these work very well in basements where you have a lot of free air and you're not necessarily worried about the coldness of the discharge air as much. However, obviously in most of multifamily buildings, most apartments, we don't have basements to work with. So how do we deal with this? So, really considering all these factors, this is a diagram of just a simple residential apartment with a mechanical closet that you might see a heat pump water heater in. Now, how do we do this efficiently? Well, for one, I kind of mentioned this, do not do this. Do not shove it in a closet. You can also see here that there's an electric resistance space heater heating the air around the heat pump water heater. This is also not the first instance where I've seen electric resistance space heating where a heat pump water heater is located. The heat pump water heater is pulling its heat from the air. If the air is heated with electric resistance, you're essentially heating your water with electric resistance. So these are some of the do nots that I really want to highlight. Some of the do's, though, ducting the intake or return, at least one of these at a minimum, or both, which might be more optimal, to the apartment. So you can see some photos here of this being done. Now, this allows the unit to breathe and have more air available via any sort of register that you're pulling it from. Now, things to consider is if you're ducting the return of that unit to an apartment, keep in mind it's discharging air at 15 to 20 degrees colder than the natural air in the room. So you do not want to design that in a way that it's dumping that discharge air onto residents, or they might complain that it's cold, they're uncomfortable because of cold air drafts. So, but this is a good first step, is ducting the unit at least on one side, if not both sides, the supply and the intake and the return, to help maximize efficiency. You could also do this approach where you have your heat pump water heater in the same closet, but the closet is actually off of, or gets access from the corridor, and you duct the intake or return, or both, into the corridor. I think there's a lot of merit in this approach. You don't have to, from a maintenance perspective, building operators don't have to get into every single apartment to do maintenance on it. They can operate on it right from the corridor itself. Corridors are also, people walk through them, but in the wintertime, people are usually wearing jackets, and in the summertime, people don't mind a necessarily cold blast of fresh air when they're walking through a corridor. And for the most part, they're only in the corridors for seconds, at most minutes. So I think there's a lot of merit to this. You also have the ability to, where you see that sort of bolded blue line around that closet, you can really make sure that, it's not only sealed from a fire code or fire rating standpoint, but also acoustically insulated, and helping deal with that issue of noise that these units create. You can kind of contain it within that little closet, and the less amount of penetrations that you have through that closet, the more you can help control the sound issue. So really, I think a great approach. And that, kind of the last thing I want to talk about is sound. So there's been a recent development of new products that are on the market that hit noise ratings less than 50 decibels, or dBA particularly. I've seen units get down to about 45 dBA. Now, the thing to consider when you're looking at a noise rating of a piece of equipment or whatever it is, really, is a change in 10 decibels is perceived as a doubling or halving of sound level. So it's not linear, it's actually logarithmic. So really a unit that's rated for 55 decibels or dBA is perceived as being twice as loud as a unit that has a rating of 45 dBA. So that 45, the units that get to sub 50 dBA is really a big improvement, huge improvement. And again, helping improve the comfort of apartments that have these in-unit water heaters. All right, now what about central systems? So, a lot of times in especially urban environments, I work a lot in New York City, Boston as well. Central systems are really what we see most of. So how do we deal with these technical challenges? Well, again, with central domestic hot water systems, the key to maximizing efficiency is to minimize resistance. That sounds very familiar to what we just mentioned for decentral. So we're dealing with the same issue here, but in a different way with central systems. And really the key is that, what we're seeing with central domestic hot water heat pumps is that they're using CO2 refrigerant for these units. And these units require cold inlet water temperature. So anywhere from 50 to 80 degrees Fahrenheit, could be somewhere outside of that range slightly. But in short, what they can't do is they can't heat the water from the domestic recirc return, which comes back to the hot water system at about 100 degrees Fahrenheit. So what happens is these units have what's called swing tanks, i.e. electric resistance swing tanks. And those are the tanks that essentially make up the recirculation losses. This is a technical challenge, one that I have not seen solved with any sort of innovative piping method or other solution yet, additional heat recovery, that sort of thing. There's probably ways around it, but the reality is that the systems that are being designed and installed right now have these swing tanks. So we have to be super aware of how to minimize recirculation losses in these hot water pipes for central systems. So how do we do that? Well, efficient recirculating pipe layout is one of the most important first steps. So what you're looking at here is a very Fred Flintstone diagram of a central hot water recirc system. You have a boiler, or let's say a heat pump water heater on the roof here, and it's providing hot water down. We call it express, is sort of the big pipe that runs the water down to a horizontal network that distributes water to apartments. And then you see a set of hot water send risers, which is the red, going up at an apartment cluster, doing a U-turn once it gets to the roof line, coming back down that same cluster in a new pipe. It's the same pipe, but it's the return portion of that recirculating pipe. Come all the way back down to the first floor, find its way back to the express return pipe, goes all the way back up to the boiler. Followed the diagram, not my words. Probably not explaining it very well, but this is called a three-pipe design. You have a hot water send, a hot water return, and then of course you have your cold water. So those are 3 pipes. This is not very good design. A way to do this better, and keep your eye on the graph or the chart here when you see me change the slide, is to move one of those horizontal loops to the roof line, or you could do it kind of vice versa, depending on the orientation vertically. But nonetheless, by doing this, it's called the box design. You're reducing about 40% of the piping for hot water recirculation, which means market improvements in reducing recirculation losses. So the way you do this is you have a horizontal loop, let's say here at the roof line, distributing to the apartments. You run down the stack of apartments to your return loop on the first floor, and that collects back to your recirc express return, back to the heat pump water heater, and you're saving on all of those hot water return pipings in the riser clusters. So this is one of the biggest ways to help reduce recirc. But really, right now where we're at with buildings designing central domestic hot water systems, we have to really consider the electric resistance swing tanks and how to minimize recirc losses, because they can be up to 40% of the entire domestic hot water load if not dealt with properly. All right, so the last couple things here I want to talk about are just some new, exciting things, a lot of which we've chatted about in the chat already, but going fully electric with space heating. So, one thing that we're thinking about a lot here at Stephen Winter Associates and really in the industry is how do we do space heating with little to no central refrigerant piping which can have some potential implications with refrigerant leakage that obviously, as many of us know, have drastic impacts on our climate with greenhouse gases. So, what are alternatives to central refrigerant-based systems? Well, one that we've gotten some exciting developments on is a packaged terminal heat pump. So, right now we've been talking in the chat about ice air units and EPACA. Those are really the two right now that we feel comfortable recommending on a project. But it's possible. And, you really just need to think about specifying airtight units that are insulated or thermally broken to help mitigate the two biggest drawbacks of PTHPs, which are they're a thermal bridge in the envelope and they're not conventionally airtight. So, we're helping work with some manufacturers to help achieve units that meet these levels of performance that are suitable for passive house. And we've gotten some great improvements, I think, over the last couple of years. And we're starting to see projects that actually have these spec'd and starting to get installed as well. So really great developments there. And then lastly, hydronic-based approaches. So, instead of having central refrigerant piping throughout the building, having central water piping throughout the building. So a couple of really key concepts here is in this approach, you have a central plant, which some examples could be an air to water heat pump or a geothermal well or loops. And that central plant is combined with not only the hydronic loop itself or the piping for that, but also the terminal units. So some examples there, water source heat pumps you could do really a mild temperature water loop, which is great, 70 to 90 degrees Fahrenheit water running around your building. With water source heat pumps taking water from or taking heat from that loop. You could do fan coil units, which would require a little bit warmer and cooler temperatures for heating and cooling. Hybrid fan coil units, which act as a fan coil in heating and a heat pump or a air conditioning unit, essentially, in cooling. But also it offers this ability to have a water-to-water heat pump tied to that hydronic loop, where you can use that the energy stored in that water as heat for your domestic hot water system. And then you're not dealing with some of the challenges that are presented with air source heat pumps. So really exciting stuff. We're seeing projects that are implementing both of these approaches now. And I wanted to just highlight that these are happening and we're seeing these developments move towards efficient electrification and electrification that is not only focused on high COPs, but also low embodied carbon and then low carbon in general emitted by these buildings. So exciting stuff. I know I talked very fast. I wanted to get through this and give Paul enough time to talk about all of his exciting work. And please reach out if you have any questions, and I'm happy to continue the discussion in the chat. So thank you.
Let me get started. My name's Paul. Thanks everyone for being here. Appreciate all the other panelists' input too. It's really great to see all these fantastic project examples. So I work for our state energy office, the Department of Energy Resources here in the Commonwealth of Massachusetts. My role is building decarbonization. So my perspective is looking across whole states and regions and helping ensure that on a state level, we're decarbonizing our building sector. So what I'd like to share this afternoon is this kind of notion of grid-friendly electrification, and using thermal codes and passive house as the tool to achieve grid friendliness. So let me dive into what I mean by that. I think you know the backstory here. So what's going on in the background is states all around the United States and countries all around the world are adding lots of renewable inputs to their electric grid. So that means in the future, the emissions footprint of a kilowatt of electricity will be lower and lower with each year. And by 2040, 2050, the emissions rate of our grid will actually be almost negligible in many places because the electricity will be mostly produced by renewables. So that's kind of part one background. And part two of the background is, the last 10 years, really, we've seen the emergence of cold climate air source heat pumps. And these have efficiencies that are quite good down to the lowest temperatures anywhere on Earth. And that allows us to unlock the ability to do building space heating with electric heat pumps, which didn't used to be possible, not that long ago here in cold climates, but now it is. So the convergence of those two things, got all of the policy folks that are looking to decarbonize states all excited because it allows a pathway to decarbonize space heating, because traditionally we've always been sort of forced to use fossil fuels for space heating. So we can get off fossil fuels and onto decarbonized electric by virtue of heat pumps, right? So that's kind of the backstory. And as a result of that, we're all rushing headlong towards electrify everything based on these two things. But there is a bit of a hiccup here. And that is that the energy codes that are available for states across the US and provinces in Canada and other locations, these model codes that are adopted, these are developed by IECC and by ASHRAE. Those model codes are not very good at thermal performance of buildings. So I'll get to the punchline here that if we build our buildings and we just build them the same way that we've been building them, even using the latest model codes, the only change we make is going from gas to electric space heating, we will have peak electric use on the grid that is way higher than is maybe necessary. So just as a simple example, this is a school project in our climate here in Massachusetts. And if I go to the far to the left, the blue bar represents the load on the electric grid due to space cooling of the school in summer. And that imposition on the grid, if you will, is about 50 kilowatts. And in the winter, we would be, in the past, up to recently, we would space heat that building with gas. And so the load on the grid in winter was 0 for the load associated with space heating. Now, if we just build that school as using the same model code that's available to all the states, IECC and ASHRAE, and the only change we make is that we now use heat pumps, we have that middle pair of bars is what we see. So the space cooling peak load doesn't change. It's still about 50 kilowatts. But you can see the load from the space heating is 200, up from 0. That's 4 times bigger than the space cooling. So the utilities that own the electric grid, this is what they're using in their calculations as they figure out grid modernization to accommodate our future all-electric world. So of course, they're doing grid modernization for a bunch of different things. We have EVs going on, EV vehicles, et cetera, but a big part of it is the swap to heat pumps. And this is the model that's being used because just the only change being made is that swap from gas to heat pumps. This is going to be really expensive to modernize our grid to accommodate these very large new peak loads if you were to do it this way. So I consulted with our grid modernization people to ask them, how much is grid modernization costing us? That's things like new substations, new poles, new wires, new metering. So in the period between 2022 and 2028, the state of Massachusetts, and we're a small state, we've already spent 1.7 billion on grid modernization. And the pace of grid modernization will continue for decades. And the rate of cost is actually going to increase from this pace of spend that we have so far. So it's going to be extremely expensive if we just keep using these model energy efficiency codes. So I spent a number of years working in IECC on the committees. And the reason why that IECC and ASHRAE are not very good at thermal, it's not set up well for thermal performance, is that everything in ASHRAE and IECC is done through the lens of how well it improves the total energy use of the building, the total EUI. So for example, someone puts a proposal together to improve, the windows or the wall performance. They would analyze that and they'd ask themselves, how much did that improve the overall EUI? And that's the only metric used. So that doesn't really result in great thermal performance. What matters in terms of grid friendliness is not only the total EUI, but also even more important is the part of the energy use, the part of the total EUI that is space heating. Because that's the thing you're swapping that used to be on gas is now on electric. And what is terrific about Passive House is that for decades, Passive House has been all about addressing thermal performance of buildings. So if we borrow the lessons that have been learned from Passive House practice and we apply them to our model codes, we find that we can really crush the space heating to oblivion, just like Passive House crushes space heating to oblivion. And that's going to unlock the ability to do electrification across the state, across the nation, across the world. It'll allow us to switch off gas and go on to electric heat pumps without causing huge new winter peaks. And that's the pair of blue and red that you see there on the right side. So Passive House is the key, and thermal codes are the key to do electrification worldwide in all our cold climates without having us to spend hundreds of billions of dollars, if you added up all the states, on grid modernization. So I like to, my latest mantra in the office here is that thermal codes and Passive House are grid modification, are grid modernization. So we think of grid modernization as, again, new substations, new poles, new wires, right? But I'd like to expand that universe and think of Passive House and thermal codes as another way to achieve grid modernization, because we're reducing the demand of the building in the first place and then don't have to make those infrastructure changes in our wires. And we get better buildings, resilience, comfort to boot, which we're not getting if we just spend it on substations. And then a kind of larger question that every state and every country and every province should ask itself, the analysis that really needs to be done at the policy level is, what is less expensive? What's more cost effective? Is it better or more cost effective to incentivize Passive House? Or is it better to buy a new substation? I mean, a substation costs $500 million. So I want you to just let that sink in and think about how much Passive House that could buy. So it's really important to analyze these things globally. So what are the particulars in the code that we need to amend from the model codes that are available from ASHRAE and IECC? It's these four things, right? Envelope, air infiltration, ventilation, energy recovery, and thermal bridges, right? So if you work in Passive House, that's like you're yawning right now. You're like, that's the oldest news in the world, right? But these are really the four things that it takes to crush the space heating and achieve grid friendliness. And I just want to point this out, it's really important because IECC and ASHRAE, the model codes that all the states adopt, they sort of do everything except these four things. So for example, in ASHRAE, there's a pathway that allows you to trade off your envelope performance with no limit. Again, because the only metric is total energy use. So if you can show that you improved your lighting so much that allows you to water down your envelope performance, that's allowed in our current code, in our current model code. That's not going to help our grid modernization efforts. Air infiltration, good news here, IECC 2021 did adopt much better air infiltration rules and testing. So that's maybe one thing that's making good progress on there. Ventilation energy recovery and the model codes, very low expectations for performance, lots of loopholes. The one that amazes me though is thermal bridge mitigation. IECC and ASHRAE still explicitly allow you to put a metal girt to go from the inside of your building to the outside of your building with no thermal break. And you don't have to do anything to consider that. It's actually explicitly allows you to do that. Kind of boggles the mind as people that have studied physics, right? That we're still allowing our buildings to ignore thermal bridges like that. So the solution for states is you should adopt those codes. That's what's available, but you have to amend them to include these 4 things. So I just thought I'd wrap up here with maybe a discussion about tactics. So if you're all passive house people and people that care about buildings in your states and provinces and countries, if you have an opportunity to be involved in advocacy in better building codes, so here's some things to consider. So, we learned a long time ago here in Massachusetts that it's really hard to do ambitious code changes on a statewide basis. So the tactic that really works is to allow to create a tiered code. So you create like a tier 1 and a tier 2, and you allow the states, the localities, the municipalities and cities within your state or province to be able to choose one of the tiers. And then you make one of the tiers base code that everyone's used to, so no one can argue with it. And you make the other tier the more ambitious thing. So for example, thermal code stuff in passive house. And then you say, if for folks, if they think that's too ambitious, you can always just say that this is a totally up to the cities and towns to decide which tier that they can be on. And it becomes a really great way to introduce more ambitious stuff into your code. So Mass has been at this for a while. So we happen to have 3 tiers. You don't have to have 3. Our base tier is just straight up model code with very few changes. Our second tier up is a stretch code, which is the model code plus the 4 thermal pillars. And then we have this specialized code, which is the same, but it adds passive house mandates for certain situations and some electrification. So again, states can do it differently than these 3. So just wanted to point out, what we're very lucky, we've been at this for a while. There's very few places that are still on the base code, pretty much universally on at least the stretch code, and in many places now the specialized. So we have almost universal thermal codes here in Massachusetts. So that's really going to help our grid modernization. But this was a model for a state maybe that's just starting this, is again, you don't have to have 3, maybe just have 2. But again, use that tactic, have a base code that is what people are used to, and then have a stretch code option for cities and towns to adopt that contains at least the 4 thermal pillars, and put passive house in there if you can, maybe have it as an option or have it for limited types of buildings, but whatever you can do to adopt passive house and electrification. So let me just end with a quick roundup. So, the headlong movement to electrify everything. If you do that without thermal codes, electrification of buildings is going to be very costly on the grid. It's going to be a cost that can be easily avoided. The model codes that we use in the US, they're not grid friendly. They do not do thermal performance well. And that's going to create very expensive grid modernization costs. So the solution is to add the 4 pillars as amendments when you adopt those codes, and then you'll have a thermal performance code. Whatever you can do to adopt passive house as much as possible, and make use of tiers to allow local jurisdictions to have a choice to adopt just the base code that people are used to, or opt into more ambitious stuff. And that seems to be very effective. So thanks very much for the opportunity to be here. really appreciate everyone's participation in this. Thank you.
One thing that kind of tied everything together, but then didn't completely, is the domestic hot water. And I'm curious, one, Bruce, who's making, you said those hot water heaters are available now in the US, but
Yeah, they're not every state has them, but all the Northeast states and New York have, and
who
California.
makes them?
Mitsubishi. It's called the
Oh, it's
Heat,
Mitsubishi.
the Heat 2.0. Uses CO2 as a refrigerant. And I responded to in the chat to Dylan, but we did have initially a problem with our swing tanks going on. All we had to do is turn the valve on the recirc line at halfway, and it stopped happening and everything works perfectly. So it's all these things require a little commissioning, but and I can't underestimate the importance of that, because I think about it every day. There's always something we can do to like our designers designed the building to ASHRAE standards, which requires 2 air changes per hour. Passive house works fine at 1/3 of air change per hour. So we've just gone in and cranked down all of the ventilation rates by 1/6, and we're seeing some savings there. So it's a learning process for us.
That's fantastic. Great news. And Dylan, with the hot water, it was interesting Bruce brought up the swing tanks from his project. I mean, how do you see in these shifts and new issues are coming up, but we're also dealing with them? Do you see trends emerging? Like, I mean, you spoke to a bunch of options. I mean, there weren't a million options. So, but in terms of, building owners like Bruce, who are pretty sophisticated and thinking ahead, do you see more one approach over another regarding domestic hot water emerging?
I still think it's very locational driven. So in New York City, it's a central system, and if it's electric, it's an air source heat pump water heater. There's a couple of instances where we're seeing some water source systems, but I think that's the trend that I'm seeing is in New York City, central air source heat pump water heaters, which have these swing tank issues. Other areas, maybe, let me just, not to call out any areas, but like a greater DC, Washington, DC, more used to in-unit systems. So in there, it's more about designing the decentral approach or the in-unit heat pump water heaters more efficiently. Even in Massachusetts, we see a lot more in-unit water heating systems compared to what rate of that we see in New York City. So the trends follow the locational norms. People are going to do what they're used to doing. It's just they're applying new technology to what they're used to doing and running into new technical challenges.
I see. Interesting. And so it's not, because we've had these conversations in Massachusetts as well, this idea of shifting to centralized hot water. But the owner's good. It really comes down to how people are used to billing for hot
Right.
water.
That's a huge, right. Exactly. That's so much related to it is the metering aspect of it. And that's usually one of the main drivers as to central or decentral. And then the decision is, okay, figure out how to do it electrically and efficiently.
Fantastic. So hot water in Massachusetts, Paul, we've got the space heating demand crushed to oblivion. What is Massachusetts going to do about the hot water?
Yeah, that's a good question. I mean, we have a lot of passive house built in Massachusetts now, and I'm going to just take a guess. I bet you 90% plus is air source heat pump space heating with gas water heating, which is like, that's just the combo that's used again and again. It's been that way for, half a decade. So what's great is, so I was just thrilled to see Dylan have a big part on electrification of water heating, because that is kind of the last piece of the puzzle. I mean, it really is like doing air source heat pumps, 10 years ago was like, people would be screaming from the rafters like, holy cow, the sky's gonna fall. And then that just all became normal in a matter of a couple of years. And then doing passive house was like something like from, maybe this was this unusual standard, from Europe, and that all just became normal in a matter of you know, a couple of years. But water heating still, I think that the state of practice right now is gas still, if you have big multifamily, because there's just not enough experience with the architecture and the nuances of design you need to think of for doing in unit. And then the central stuff, that equipment is all kind of newer. So people are just getting used to it.
It's available. Actually, you know, to be honest, when we went to contract, it wasn't available. We had a gas. It was sort of the last. That was the gateway drug to our electrification, is being able to get these Mitsubishi Heat 2.0 units. But once we had that, there was no reason to bring in the gas service. But they're great, and I just can't say enough about them. No maintenance. I think, you know, the money you save on the bringing the gas service in, maybe that's you know, there's a premium to put them in, but they're great. And, you know, they make smaller versions. We've been involved with apartment buildings where we charge for hot water, but you can put little low voltage, actually radio operated little water meters in. So there's a solution out there people are looking for.